Let's start with a simple atomic structure. For a simple atomic structure, we have a core at the center, and there are protons inside the core. And we also have electrons. Electrons are orbiting around the core. So these are electrons with negative charge. This is another electron with negative charge. So on and so forth. Okay, now let's talk about rules. First rule is each level has a specific energy, and they increase by moving away from the core. So in this case, we have 3 levels. This is the lowest energy, this is the highest energy. Okay? This is the first rule. And the second rule is electrons can't move here. They can't move between energy levels. So electron is here or here or here. Nowhere in between. Okay? So everything in between is forbidden. They can't go there. Now, what it means if you give this electron enough energy, they can jump. But there is a specific energy. Now let's look at this example. Let's say we have one electron and somehow we put this electron at this highest energy. Okay? So we have one negative electron at the highest energy here. So this electron is not stable at highest energy. This electron loves to jump to lower energy. So if we release this electron will jump to lower energy. Okay? But there's a problem here. You're jumping from higher energy to lower energy, but we have conservation of energy. What happens to this energy? Well, this energy is released as a photon or light. How much energy is inside this photon? It's exactly the same energy difference we have here. And each energy corresponds to a specific color. Now let's say because this is a big jump, we have high energy, so this will produce a blue line in our spectrum. We could release this electron from this state, and in this case, this will be the result. Another possibility is this electron can jump from here to here, then from here to here. Depends on the situation. So at the end, we will have different colors and different lines going to lower energy. Let's say this is okay. So it looks like kind of rainbow, but just lines. There's nothing in between. This is called emission spectrum. Okay, so basically these are different photons jumping with different levels. And what is interesting is this structure depends on element. So hydrogen has a different structure compared to helium. They have different energy levels, they have different number of protons, different number of electrons. So what it means This emission spectra works like a fingerprint. Each element has a unique configuration of colors and lines. And that's the main tool we use to identify different elements. Okay, now let's look at this interesting case. This is another case. Okay, now we have a hot object, in this case like the sun. Because this is very high temperature, particles are moving very fast. But most of them have the same energy. What happens in this case, they collide, they produce photons. Because most of them have the same energy, you will see one common energy at the highest intensity. But we also have small fraction of particles moving faster, and these particles can produce higher energy. So we also have higher energy in this spectra, but it's not as intense as our average energy. At the same time, we have particles with lower energy. These particles are moving slower. Again, not as many as average energy, but we can see those particles in the spectra. So this is our spectra. We plot intensity versus energy. So we have common energy or average energy at highest intensity, and we have higher energy and lower energy at lower intensity. In terms of spectra, each energy corresponds to a color. So if we use a device to analyze this spectra, what we see at the end is something like a rainbow. We see all colors continuously. They start from violet, blue, and they end around red in this case. But be careful, this is just optical part of this spectrum. Basically, we have very high energy and very low energy, but our eye is not sensitive to that part. So if we have X-ray, we have gamma ray at higher end. We also have infrared, microwave, and radio waves at lower energy. This is just optical part. You can also see each color corresponds to a specific energy. In this case, you see red is lower end and blue and violet are higher end of the energy. So this is one configuration. Another configuration is, let's say we have this hot object at the center, but there's cooler cloud surrounding this object. This is still hot gas, but it's not as hot as the core. What happens in this case, we have atoms moving around, and for atoms, you remember we have atomic structure. There is a core, electrons are orbiting around the core. But electrons have a specific energy level. This is lower energy. Moving away from the core, we have higher energy. Electrons love to stay at the lowest energy. Okay? Unless you give them the energy. So this hot object produces a lot of photons. And remember, different energies. If one photon has enough energy, then this electron can absorb that specific energy and jump to higher state. Okay? So let's say I have 5 photons here. This is just a cartoon. And one photon has enough energy for this energy jump. So what happens in this case is electron will absorb that energy. We have conservation of energy, so this electron has higher energy right now. It will jump to higher energy. At this end, you will see all photons we had before, but one of them is missing. Okay? Of course, we have billions of photons moving around here, and we have a lot of different energy levels, and sometimes we have different elements. So what happens at the end, again, we see this rainbow structure, but in this case, because photons are missing, some photons are gone, so you will see these black lines in the rainbow. So this is called absorption spectrum. And if we draw our intensity and energy, what happens in this case, remember our previous energy was like this, but now photons are missing. So this is missing photon, this is missing photon, this is missing photon. We don't have this photon. Okay, so it looks like something like this. So we have absorption spectrum. Another interesting result is, so let's say we have this continuous spectrum, and if you remember higher energy, lower energy, I just put colors here, red one side and blue and violet on the other side. Okay, and in this case we have kind of all colors, but you can see our highest point is around green, so this object will look like green. Okay, now let's say I decrease the energy. So if I decrease the energy, the average dominant energy or average common energy will move to lower energy, so it will look like this, right? So this is lower temperature or lower energy, and you can see in this case orange is dominant. If you move to lower energy, it will look like this, and you can see in this case red is dominant. On the other hand, if I go to higher energy, my average common energy will move to higher, so it will look like this. Okay, so this stuff is blue. So this is energy or temperature. Increasing energy or increasing temperature will result in shift in this spectrum, and this shift means a different color. Okay, that's the main reason if we compare stars, a red star and blue star, we can say red star is cooler than a blue star without any measurement. Okay, so what's the difference between emission and absorption? The main difference is, in one case, electrons jump from lower energy to higher energy. So this is one case, electrons jump from lower energy to higher energy. So they need to absorb some kind of energy to get to excited state. So this is, they have to absorb. This is absorption, right? And another example is electrons jump from higher energy to lower energy. So they have to emit this energy. They have to emit this energy. That's the main difference between absorption and emission spectra. In one case, electrons jump from lower state to higher state. They absorb energy. In another case, they jump from higher state to lower state. They emit this energy. In absorption, we have full spectrum, but few lines are missing. In emission, we only have those lines. So they kind of opposite to each other. Now let's talk about the relationship between colors, energy, and wavelengths. So if you remember, we have red in one side and we have blue on the other side. So in terms of energy, this is higher energy, this is lower energy. It's the same for temperature. This is higher temperature, this is lower temperature. In terms of wavelengths, this is longer wavelengths and this is shorter wavelengths. So basically these waves are longer. So wavelengths is the distance between two similar points. Okay, now let's talk about Doppler shift. Doppler shift is basically changing the wavelengths when you move away or towards an observer. Okay, so let's say we have a light source. In this case, there is no motion, and this is our observer. So nothing is moving. We see this is spectrum. In this case, just 3 lines. Now, what happens if this light source starts moving away from us? So if it starts moving away, in this case, the wavelengths will stretch. So it means all lines will move towards red. Okay, so this blue supposed to be here, but is shifted towards red. This yellow supposed to be here, but it's shifted towards red. This red supposed to be here, but it's shifted. Okay, so this is called redshift. If this light source starts moving towards us, this is the opposite case. So this blue is supposed to be here, but it's shifted towards bluer. Yellow is shifted towards blue. Red is shifted towards the blue. You see, this is the change. So this is called blue shift. What's more interesting is this shift, when you compare the shift with the original wavelengths, you can determine the speed. You can say how fast this object is moving. So for higher speed, we have larger shift. Okay? So velocity or speed is equal to c times delta lambda divided by lambda. Okay, so this is the speed, how fast this object is moving. This is the speed of light, which is 300,000 kilometers per second. This is the shift, and this is original wavelengths. Okay, so this is basically the shift. So for example, you have 5 angstrom shift for 6,000 angstrom. Okay, so your original wavelength is 6,000, your shift is 5 divided by 6,000 times 300,000. That will give you velocity. Okay, And because you're using the same unit for lambda and delta lambda, velocity is kilometers per second, just like c. This is extremely important to calculate the speed or velocity of different objects in the sky.